Today, we're going to strip away the guesswork and dive into the hardcore engineering behind slip-yoke axial load. Listen up, techs and engineers, because this is absolutely where you elevate your diagnostic logic. We're going to look at the invisible forces that are quietly determining the lifespan of the transmissions, drive shafts, and seals that roll into your bays every single day. Let's get into it.
So, here's our agenda for today's masterclass. 1. Physics of axial load. 2. Spline mechanics and materials. 3. Drive shaft angles and lifts. 4. Lubrication and seal survival. 5. Diagnosing driveline NVH symptoms. And 6. Field inspection and maintenance. Okay, kicking things off with Section 1, Physics of Axial Load, the Invisible Force. Right off the bat, we need to redefine how we view this driveline component. It's not just a passive slider, It's an active, highly stressed mechanical interface. The crucial point here is understanding the real difference between the torque that's twisting the shaft and the axial force that's trying to literally shove the whole driveline forward or backward through your transmission output seal. The slip yoke has to accommodate suspension compression, frame flex, and torque reaction, all while sliding axially under massive pressure. If it can't move smoothly, well, that axial thrust is transferred directly into your transmission output shaft and tail housing bushing. And remember, that bushing is designed to provide rotational support, definitely not to resist dynamic lateral plunging forces. And the math brilliantly illustrates the physics behind all this force. When we look at the cosine force formula, axial force equals the tangential torque force times the tangent of the U-joint operating angle. What does that actually mean for us in the shop? It means even a perfectly balanced drive shaft generates oscillating axial thrust, simply because universal joints don't transmit constant velocity at an angle. That rotational velocity fluctuation creates a cyclic thrust. Now, at a perfect 1 to 3 degrees, it's totally manageable. But as that operating angle increases, this force spikes exponentially. There's just no getting around the math. Moving right along to Section 2, Spline Mechanics and Materials, the active interface. Now that we've mapped the physics, let's step into the laboratory and talk metallurgy. Understanding the splines absorbing these brutal forces is critical, especially for any custom build or heavy-duty replacement. Notice how heat treatment levels drastically impact the long-term fatigue life of the splines. Case hardening creates a super hard surface. We're talking 58 to 62 Rockwell C, but it leaves a tough core that actually risks brittle fracture at the spline roots under extreme shock loads. Actually, this is exactly why premium heavy-duty setups rely on through-hardened 4140 or 4340 chromoly, tempered to around 28 to 36 HRC. That specific range provides the optimal tooth strength for surviving that constant, punishing axial pounding. What's really fascinating here is how geometry dictates survival. Involute splines are designed specifically to minimize thrust force conversion during sliding. But here is the classic engineering trap. If your suspension droop pulls that slip yoke outward so the engagement drops below 1 times the spline diameter, your contact area virtually vanishes. Think about the formula for contact stress. You divide the force by the number of active teeth. If your engagement drops, contact stress skyrockets right past the yield strength of the chromoly, and you instantly start destroying the teeth. It's game over. All right, Section 3, Drive shaft angles and lifts, the geometry trap. Let's move to the workshop floor and talk about the absolute #1 cause of axial load failure I see in the field. Lift kits. Just a standard 4-inch suspension lift without proper pinion angle correction can easily increase U-joint operating angles by 4 to 8 degrees. Because of that cosine formula we looked at earlier, this multiplies your axial loads by a staggering factor of 2 to 4 times normal operating parameters. Literally 2 to 4 times the force. This is pure geometry escalating axial thrust directly onto the output shaft. So if you're dealing with those steep angles from a lift, you really have to weigh the mechanical trade-offs of a slip yoke eliminator, or SYE kit. An SYE entirely removes that massive thrust load from the transfer case output bearing and seal, moving the slip function to the drive shaft itself. It's brilliant for reducing driveline vibration and protecting your transfer case, though, yeah, it does require a custom-length drive shaft and definitely adds a bit of complexity and cost to the build. Let's shift gears to Section 4, Lubrication and Seal Survival, Preventing Metal-to-Metal Collapse. We need to talk about the lifelines of the system, because without proper lubrication, all that beautiful precision involute geometry turns into a literal grinding wheel. Try to visualize what's happening at a microscopic level. These splines require an elastohydrodynamic film thickness of just 0.5 to 2.0 microns. That is microscopic. If that film collapses under extreme axial pressure, or say temperature fluctuations thin the viscosity too much, metal-to-metal fretting begins instantly. This is exactly why you must select an NLGI Grade 2 moly-based grease. Please never use standard chassis grease here. It will fail because it lacks extreme pressure or EP additives. The molybdenum disulfide acts as a solid boundary layer when the hydrodynamic liquid film inevitably collapses under that heavy load. Getting into maintenance, you need the tire intervals directly to the vehicle's duty cycle. Normal highway driving? You're good for 5,000 to 10,000 miles. Towing or off-road drops that to 3,000 to 5,000 miles due to severe stress. But pay close attention to water exposure. Deep water crossings require an immediate purge. If you ignore this and let it slide, water intrusion destroys the grease's load capacity, and fretting corrosion will literally ruin the yoke before the truck even makes it to its next scheduled oil change.
Okay, Section 5, Diagnosing Driveline NVH Symptoms, Logic over Guesswork.
So how do we spot these failures before the whole component just grenades on the highway? We use strict if-then diagnostic logic for noise, vibration, and harshness. Please do not be the tech who fires the parts cannon at a differential gear whine when the real symptom is a low-speed clunk on takeoff. That clunk is classic spline lash, and it's exacerbated by axial load reversals. Furthermore, axial load induces a very specific second-order harmonic vibration. That means it cycles at twice the driveshaft RPM, producing a drone that changes under load versus coast. You have to differentiate that from the constant gear whine of a failing differential. When you have the parts on the bench, look extremely closely at the spline teeth. Do you see bright polished wear? That is dead giveaway proof of fretting wear from axial oscillation. And listen, if you find an output seal leak on a recently lifted rig, do not just pop a new seal in there and call it a day. Look specifically for seal lip inversion or rollover. That is an absolute, undeniable indicator that dynamic axial stress is shoving the yoke too deep. You have to fix the geometry, not just put a Band-Aid on the symptom.
Finally, Section 6, Field Inspection and Maintenance, the checklist.
Let's outline the exact rigorous sequence you should be running on every rig that hits your bay. Follow this step-by-step logic gate. First, do a proper grease purge. Pump the fitting and look closely at what comes out. Milky, you've got water contamination. Second, verify the engagement length at normal ride height to ensure you have enough active teeth. Third, radially test the yoke for lash using a dial indicator. If you measure 10 to 15 thousandths of an inch of play, you have significant spline wear. Fourth, check that output shaft seal for lip inversion. And hey, while you're in there, check for shaft scoring and output bushing wear. That helps you differentiate between just a worn spline and a fully collapsed transmission tail housing bushing.
And here is your absolute drop-dead engineering tolerance limit. If you measure a radial lash exceeding 0.025 inches, 25 thousandths, that slip yoke is dead. Done. Do not repack it, don't try to save it, replace it immediately. Before the resulting galling and severe vibration, take out the transmission output shaft entirely. So I'll leave you with this provocative thought. Slip-yoke axial load is the invisible force determining the lifespan of the entire driveline. Now that you understand the formulas, the metallurgy, the spline mechanics, and the real-world diagnostic indicators, are you going to use this engineering logic to permanently solve the root cause on your next build? Or will you just keep replacing blown seals?